Welcome to another example of operations scheduling where we will look at sequencing n jobs on m machines. So in the previous examples that we have seen, we saw how to sequence n jobs on 1, 2 and 3 machines. In this example, we will see how to schedule n jobs on more than 3 machines. So the table below gives the processing times, which is in hours, of 7 jobs to be processed on 4 machines, M1, M2, M3 and M4, in the order M1, M2, M3, M4. So basically these are the various jobs which need to be processed on M1, M2, M3 and M4. And the way these have to be processed is that each of these jobs has to be first processed on M1, then on M2, then on M3 and then finally on M4. Now what we are being asked to do is to sequence the given jobs using Johnson's method and find the overall processing time. So now we have to find out in which sequence should we process these jobs so that the overall processing time is minimized. So let's see how we can use Johnson's rule in this case. Now Johnson's rule can be applied for sequencing n jobs on m machines. However, there are certain conditions which need to be fulfilled before we can use this rule. Let's say there are m machines which are M1, M2, M3 and so on till M. So there are total m machines. Now the two conditions which need to be fulfilled are: first, minimum processing time on machine M1 should be greater than or equal to the maximum processing time on machines M2, M3, M4 and so on till M minus 1. So minimum processing time on machine M1 should be greater than or equal to the maximum processing time on machines M2, M3 and so on till M minus 1. So this is M minus 1. So this is the first condition. So it's either the first condition or the second condition, which says the minimum processing time on machine MM should be greater than or equal to the maximum processing time on machines M2, M3, M4 and so on till M minus 1. So minimum processing time on machine MM should be greater than or equal to maximum processing time on machines M2, M3 and so on till M minus 1. So let us understand this in a little detail. So let's say there are three jobs, A, B and C, and there are M machines, so M1, M2, M3, M4 and so on, and the last is M. Now the first condition says that the minimum processing time on machine M1. So this is M1. So first we'll find what is the minimum processing time for these jobs on machine M1. That should be greater than or equal to the maximum processing time on machines M2, M3 and so on till M minus 1. So this is being compared with the remaining machines except the last machine. So the minimum processing time on machine M1 should be greater than or equal to the maximum processing time on machines M2, M3 and so on till M minus 1. So out of these remaining machines, whatever is the maximum processing time for these jobs, that should be compared to the minimum processing time on machine M1. That is the first condition. The second condition is the minimum processing time on machine MM. So now we are taking the last machine, which is this, and we'll note the minimum processing time on this machine for these jobs. Now that should be greater than or equal to the maximum processing time on machines M2, M3 and so on till M minus 1. That is again the same thing. So we'll compare with the maximum processing time of all the machines except the first machine and the last machine. So we'll take the maximum processing time on these machines for all these jobs, and for this condition to be met, the minimum processing time on machine MM should be greater than or equal to the maximum processing time on machines M2, M3, M4 and so on till M minus 1. So if any of these two or both of them are met, then we can use Johnson's method to solve the problem of sequencing n jobs on M machines. So let's say that one of these conditions or both of these conditions are being met. So now what Johnson's rule would do is it will consider two hypothetical machines, X and Y. So the jobs are A, B and C, and the machines will be X and Y. The processing time of various jobs on machine X is the sum of the processing time of the jobs on machines M1, M2, M3 and so on till M minus 1. So for X, the processing time is the sum of M1, M2, M3 and so on except the last machine. So this is the processing time. We'll add up the processing time for all these machines for each of the jobs and we'll note it against machine X. While the processing time of various jobs on machine Y is the sum of the processing times of the jobs on machines M2, M3, M4 and so on till MM. So here we'll skip the first machine and we'll take the remaining machines and we'll add up the processing times for all these machines M2, M3, M4 and so on till MM, and we'll note it down against machine Y for all these jobs. After this has been done, then we can use Johnson's method for sequencing n jobs on two machines to solve this problem. So let's see how we can solve the problem at hand using this method. So this is the information that has been given to us in this example. We have 7 jobs, A, B, C, D, E, F and G, and we have 4 machines, M1, M2, M3 and M4. And we have been given the time in hours for processing each of these jobs on these 4 machines. Now, in order to solve this, first we have to find out if the two conditions for applying Johnson's rule are met or not. So the first condition is that the minimum processing time on machine M1, so minimum time on M1 should be greater than or equal to the maximum processing time on machines M2, M3 and so on till M minus 1. So let's find out the minimum processing time on machine M1. So here the minimum processing time on machine M1 is 2. So this is 2. And let's find out the maximum processing time on M2, M3 and so on till M minus 1. So in our case, M is 4. So M minus 1, this becomes M3. So basically these two machines. So the maximum processing time for these two machines is 8. So definitely the minimum processing time on machine M1 is not greater than or equal to 8. So this condition is not met. Now let's see if the second condition is met, which is the minimum processing time of the last machine, which is M4, should be greater than or equal to the maximum processing time of the machines M2, M3 and so on till M minus 1, which in our case is M3. So minimum of M4 is 8 and maximum of M2 and M3 is also 8. So this condition is met because 8 is equal to 8. So what this means is that we can use Johnson's rule to solve this problem. Now the next step is to consider two hypothetical machines, X and Y. So we have 7 jobs here, A, B, C, D, E, F and G, and we are considering two hypothetical machines on which these jobs are to be processed, X and Y. Now for X, we have to take the addition of the processing time of M1, M2, M3, that is all the machines except the last machine. And for Y, we have to take the addition of M2, M3, M4 except the first machine. So for X, we'll consider these, and for y we will consider these. So let's add the numbers. So for a, 3 plus 1 4 plus 4 8, and for y 12 plus 4 16 plus 1 17. Now for b to be processed on x, we'll add 8 and 5, which is 13. And for b to be processed on y, we will add 5 and 15, which is 20. Now for c to be processed on x, we'll add 11, 3 and 8. So 11 plus 8 is 19, plus 3 is 22. And for c to be processed on y, we will add 3, 8 and 10. So 8 plus 10 is 18, plus 3 is 21. Next, for d to be processed on x, we'll add 4 plus 7 plus 3. Now 7 plus 3 is 10, plus 4 is 14. And for d to be processed on y, we'll add 7 plus 3 plus 8. 7 plus 3 is 10, plus 8 is 18. Now for e to be processed on x, we'll add 5, 5 and 1. So 5 plus 5 is 10, plus 1 is 11. And for e to be processed on y, we'll add 5, 1 and 10, which is 16. Now for f to be processed on x, 10 plus 2, which is 12. And for f to be processed on y, 2 plus 13, which is 15. For g to be processed on x, 2 plus 5 plus 6. So 2 plus 5 is 7. 7 plus 6 is 13. And for g to be processed on y, 5 plus 6 plus 9. So 9 plus 6 is 15, plus 5 is 20. So these are the processing times for the hypothetical machines x and y. Now let's try to sequence these using the Johnson's method of sequencing n jobs on two machines. Now, as per Johnson's rule, first we have to find out the shortest processing time on any of the machines. If the shortest processing time is on the first machine, then we'll place that job at the beginning of the sequence. However, if the shortest processing time is on the second machine, then we'll place the job towards the end of the sequence. So first let's find out the shortest processing time. So here the shortest processing time is 8. And since it is on the first machine, we'll place job A at the beginning of the sequence. The next shortest processing time is 11, and that is also on the first machine. So we'll place E at the beginning of the sequence. Now since we have already considered A and E, we'll cut these lines. The next shortest processing time is 12, and it is for job F, and since it is also on the first machine, we'll place job F at the beginning of the sequence, and we'll cut this line. The next shortest processing time is 13, but we have 13 for two jobs, B and G. So basically there can be two possibilities. Either we process B first and G after B, or we process G first and then B after G. So it can be B and then G, or the second possibility is A, E, F and then G and then B. So let's cut these two lines. The next shortest processing time is 14, which is for job D. So let's put D towards the beginning of the sequence and let's cut this line. And then the last one is C. So C will be processed at the end of the sequence. So these two are the sequences in which we should process these jobs in order to get an overall minimum processing time. Now you can proceed and calculate the minimum processing time as we have done in the previous examples for these sequences.